So we're given an array of strings. Each of these strings are just simply words. Now we want to categorize each of these words into sublists, okay, that are in a parent list, and each of these sublists contain anagrams. All right, so each of these words are basically anagrams. Each of these three words are anagrams, and this is by itself. Okay. Now, to understand what an anagram is, Leetcode actually provides a little bit of an explanation, but I believe it's much more better that I explain it, because the explanation given is not that clear or concise. Basically, an anagram is any word that matches with another word in terms of the type of characters and the amount of characters. Okay, so we can see in this 3-word example list, right, we have 8, eat, and tea. So if we just count the amount of characters that we have and the types of characters we have A, which has 1, we have T, which has 1, and we have E, which has 1. Okay, so we have 1A, we have 1T, and we have 1E. If we look at eat, we have 1E, we have 1A, and we have 1T. Alright, you can see how they both are anagrams because they both have the same amount of characters and the same frequency for each character. Okay, same thing for T. Now, what this means is that the order of which your anagrams are being compared doesn't matter. All right, all we need to make sure is that each word that is being referenced to a specific other word is in the same order. Okay, so for that we can use sorted. Okay, and just remember that for later on, but that was just a little bit of a pre-context into my solution. Now, in order to actually solve this, we're actually going to be using a reference, right? And this way we can keep everything very, very efficient instead of having to do a lot of operations for each and every item before moving on to the next word, and then just keep going, right? It can get very, 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 very slow. So we're going to have a reference point where we can just basically put our word, right, and then we can see if there is an anagram for it, and then we can add it to that specific key. So if you don't already know, I'm using a hash map to achieve this. All right, and basically a hash map allows you to store a key value pair, hence why it's really, really useful for here, because we can have a sorted string which can be associated to different words. All right, so now that you know hash map is a key value pair, right, it allows you to store key value pairs, there's also additional benefits to using a hashing map, and that is that it is really, really fast. Specifically, it has O of 1 time complexity, meaning that it takes a constant time. So for example, let's say your data has 10 million key value pairs and it takes 30 operations to get to your desired result. Now, let's say your data set now has become 50 million. It will still only take 30 operations. So there is no correlation between your data set and the amount of operations being done. All right, it always stays constant. Hence why we also say that O of 1 is just constant time. All right, because O of 1 can be a little bit misleading because it looks like there's only one operation, right? You only need one operation to get to your desired result, but that's not what it's truly representing. Okay, so now that we understand all about that, how can a hash map actually achieve O of 1 time complexity on all of its operations? Well, in very, very short answer, it is due to hash. All right, or hashing, I should say. Basically, what happens is when you create a key value pair, the key is being hashed. Okay, so basically the key is computed so that it has a hash. Now, what's the whole idea of this hash? Why do we need this hash? Well, this hash is used to create or assign the key value pair to an index position. This means that this hash that we have actually created is related or correlated to the index position because it was used to create or assign the key value pair to an index position. So then if you try to retrieve data, for example, right, that's where O of n time complexity is usually used, right? So let's say you try to retrieve data. Instead of iterating over each of these of the items within the data set like you would do with an array, right, you just keep iterating until you find a your result, right, which is really inefficient because as you know, you scale out and you have more and more data, the amount of operations will really build onto each other and will lead to slower time performance. In this way of using the hash, right, we're able to keep our operations constant because all you need to do is you need to use the an algorithm which will help find an index position based on your hash. Basically, what will happen is you have the key, right? You're gonna get your data based off of that key. The key is then rehashed, all right? Or I should say actually hashed, because rehash will assign a new hash to it. But all we want to do is we want to convert it back into a hash. This hash will be the exact same as the one that we had assigned to that key value pair, all right? Then using this hash, since we use this hash to create the index position, we can reverse engineer it. So we can now say that we have this hash, find the index position that is used by this hash, all right? And then through our algorithm is able to spit out an index position so we can find exactly where the key value pair is located. So basically by using this hash, we're able to find the index position and easily locate where our data is instead of having to iterate over your data before you find a specific result. So it's literally like doing, for example, strs and then like the brackets and then putting your index position in, right? But except that you do not know the index position, all you know is the key, all right? So that's the way it's able to have O of 1 time complexity for retrieving data and things like that. So now that we understand a bit more of why we should use hash maps, specifically because of the key value relationship that we can have, right, which is something we could actually use within our use case, but also because of its very fast implementation and fast performance due to the hashing system that they use, let's go ahead and implement it. So to implement it, I'm gonna first go ahead and create a hash map. In Python, a hash map is a dictionary, so I'm just gonna say H for hash map and then just create a dictionary like that. All right, curly braces. Now what we need to do is we actually need to iterate over each of these items so that we can actually compare this item, which is going to be sorted, to a key in the hash map. All right, so we're going to compare this item, but it's going to be sorted to a key in Python. Okay, so first of all, let's just iterate over them. All right, so we're just going to be iterating over the str list. So to do that, we're going to do a for loop. So it's just going to be for I in strs. And for now, I'm just going to print the I. And let's just run this. It'll take a little bit of a time because it's running on the cloud. And you can see that in our console you could think of, you can see that it's iterating over each of these items because we're actually getting access to each specific string within the list. So now we can just use this and cross-reference it to our hash map. So to do that, we're going to actually call an if statement. And the reason for this is within our key value pair, right? You're going to have the sorted list. All right, the sorted list is just going to be the characters of the words. It's just that when you sort them, they automatically become list. So that's going to be your key. And then your value, all right, your value is just going to be a list, and in this list you're going to have the different words that belong to that specific sorted item. Because remember, when you sort it, right, and you reference it with the same word sorted, they both should be the same value because they have the same amount of characters and the same frequency of characters and same types of characters, right? So essentially what it means is that the order doesn't matter, so we can enforce a strict order so that we can just use it to cross-reference. So for I in strs, and then all we need to do is we first need to run an if statement, and I'll explain in a reason why. But actually before that, let me just go ahead and sort it out. So to sort a string, all we need to do is I'm just gonna write sort underscore I, and this is just gonna be in the sorted function, and it's just gonna contain I. But after this, I actually need to do another operation, and that operation is actually sorted underscore tuple. I'll just say tup. And the reason why we need to convert sort underscore I into a tuple is because we're actually going to be using this for our key, and our key has to be immutable, meaning it cannot change. However, when we run this, it actually makes a list. Okay, it makes a list, and a list is mutable by nature. So by making a tuple which acts like a list, all right, you can still have multiple items within a tuple, but the benefit of a tuple is that it is immutable, meaning it cannot change, which is this perfect use case for a key, right? Because a key cannot change as well. All right, and the reason for this is because it will not hash properly if you do not have it with that specific nature. Okay, so that's why we just convert it into a tuple, so that's immutable. And now we're gonna actually run the if statement, and that is if, all right, and we're just gonna say sorted underscore tup, all right, and we're gonna say in h. Okay, now what have I just written? Let me just actually indent this and I'll explain. Okay, so what did I just write? Well, I just said that if the tuple, remember, because the tuple is going to be the place of entry for our key. So all we're saying is that if this key exists within the hash map, then do something. All right, and that is simply, we're going to just add, or I should say append to the list that we created. Okay, so sorted underscore tup dot append, and we're just gonna append I because we want it to be in the non-sorted form, and string form too, by the way, because this makes it into arrays and separates the word based on the characters. So we don't want that. We want the actual word. Now otherwise, if sorted underscore tup, or the sorted version of this word, its key already exists, then what we need to, so this is if it exists. All right, so this is if the key value pair exists. So otherwise, if the key value pair does not exist, okay, if it does not exist, we first need to create the key. All right, because when we're doing this, right, when we're running this syntax, we're actually assuming that sorted underscore tup, whatever that value is already a list. All right, because we're running a list command. Okay, but if sorted underscore tup is not a list, all right, if it's null, right, dot append would not be valid. So by running this if statement, we ensure that we can initialize the value if the value does not exist within our hash map. So in this case, it's just going to be sorted underscore tup, and then it's going to be equals, so h, and this is how we just access it. All right, in this case, we're saying equals, meaning we're creating this into the hash map, and it's just going to be an empty array, and then we're going to run the same exact program. Okay, I'm just going to make sure I take care of the indenting. There we go. Okay, then we're gonna go ahead and break out of this function, right? Break out of this loop, I should say. So we just broke out of this for loop, okay? And now And now we're gonna actually return, okay? We're gonna return list, okay? Because remember, we want it to be in a parent list, right? Because you can see here that there's a list with multiple sublists, and these sublists are actually referenced in the hash map itself. All right. So it's just gonna be list and then h dot values. Values just gives us all the values. It doesn't give us any of the keys. It just simply gives us the values associated with the keys. Now if I run this code, just to make sure there's no errors, you can see it's accepted and there's only a 30 millisecond runtime. Alright, which is pretty fast considering the operations we're doing. Just press submit. And there you go.